Now that we've defined the radius and the interval of convergence for a power series, let's go through some examples so that we can see how to, in fact, find these for each power series. So the first example is the sum from k equals 0 to infinity of x to the k over k factorial. So recall that to find the radius, we must use the ratio test. So I start by finding the limit as k approaches infinity of the of the k plus first term, which in this case is x to the k plus 1 over k plus 1 factorial. And I'm going to multiply by the reciprocal of the kth term. So in doing that, again, I focus on the like terms in top and bottom. Note that as we saw in our general look at the radius of convergence, I have an extra factor of x minus 0 in absolute value here. So I factor out the x with the absolute value. And that leaves me with the limit of k factorial over k plus 1 factorial. I don't need the absolute value here because I know that my k values are positive. And if you recall, when we talked about the ratio test, we said that we could simplify this ratio of factorials as 1 over k plus 1. Now, importantly, I'm focusing on what the value of this limit is. That limit is 0. So we're left with absolute value of x times 0. And the question we're thinking of here is, when does this series converge? So the ratio test would say whenever we can ensure that what we end up with here is less than 1. But 0 is less than 1 for all x. So what we see here is an example in which we would be able to say that this series converges for all x. The radius in this instance is infinite. Again, in thinking about that, it's as if I'm taking this term that goes to 0 and dividing it over to the other side, and that reciprocal then would approach infinity. So if the radius is infinity, then automatically that means that the interval is the whole real line. So this is kind of one extreme that we can see in finding the radius and interval of convergence. If it turns out that we end up with a limit of 0 from the ratio test, that would always be smaller than 1, so we would get convergence for all values of x. Let's look at our next example. Here I have the sum from k equals 0 to infinity of 2k factorial times x plus 2 raised to the kth power. Again, same goal, I want to find the radius of convergence. So in using the ratio test, I get up top the absolute value here of, importantly, keep in mind that it's 2 times k plus 1. So I'm going to have to distribute that 2. And this would be x plus 2 to the k plus 1. And we're dividing by exactly what we see in the sum. Again, I get a factor of x plus 2 in absolute value that I can bring outside of the limits. And that leaves me with a 2k plus 2 factorial divided by a 2k factorial. Again, thinking back to what we talked about with regard to factorials when we looked at the ratio test before, I can simplify this by trying to relate the larger factorial to the smaller. And so what I mean by that is I can rewrite 2k plus 2 factorial as 2k plus 2 times 2k plus 1 times 2k factorial. Then I can cancel that 2k factorial with the one in the bottom, and now I'm left with the limit as k approaches infinity of 2k plus 2 times 2k plus 1. So essentially, we're getting this infinite limit here. And the question is, when is that going to give me a limit that's less than 1 for the ratio test? And what we can see there is that this has no value of x for which this would occur. Now we have to be a little bit careful here. So one thing that this certainly does mean is that the radius is 0. So if you get, in using the ratio test, that you get a limit of infinity, remember that the radius is defined as 1 over that limit. So again, we think about 1 over something approaching infinity, the total fraction is going to approach 0. However, this doesn't mean that there are no values of x for which the power series converges, because if you think back to the last video, we went through and looked at the fact that every power series converges at its center. So what we're trying to decide here is where else does it converge. And so in this example, we see there's nowhere else that it converges. So the interval contains a single point, and that is the center. In this case, recall that we said the center was -2, because that can be expressed as x minus a -2. Alternatively, the center is always the value of x that would evaluate to 0 in the terms of the series. So my interval I could express with curly brackets to indicate that it's just a single point. I'll also say alternatively, you could identify the interval as just x equals -2. That's fine as well. So this is the other extreme. On one hand, we saw an example where the power series converged for all x, and now we see one where it converges at only a single point. So that's the other extreme. And then one last example on this part, to think about what can happen in between. So we've seen the two extremes. And so if I look at the power series with terms 2x minus 4 raised to the k over k plus 1 squared. This was the third example we looked at. In fact, all three of these are the examples we saw when first looking at power series. And there's a few ways to deal with this, but I'll point out that we said that we could rewrite this as 2 to the k times x minus 2 to the k divided by k plus 1 squared. You don't have to rewrite it here, but one advantage of doing this, if you recall, was that this allowed us to see the coefficient, what we called c sub k in our definition of the power series. So writing it like this, I was clear that that was my c sub k. Another advantage to this is, in general, this is very clear about what we're trying to get an inequality for here. In this case, we're trying to come up with a statement about how far we can move away from the center, which happens to be 2, and that's a little bit harder to see in the original format. So I want to use the ratio test. And if I do that, then I'm going to have 2 to the k plus 1 times x minus 2 raised to the k plus 1, all divided by k plus 2 squared. And I'm going to multiply by the reciprocal, so k plus 1 squared divided by 2 to the k times x minus 2 to the k. So again, I'm looking for like terms. I'm going to notice that I can bring out my extra factor of x minus a, an absolute value. Doing so, I have x minus 2, an absolute value, limit as k approaches infinity, and we're left with here 2 to the k plus 1 times k plus 1 quantity squared over 2 to the k times k plus 2 quantity squared. Again, it's safe to drop the absolute value here because what I'm taking the absolute value of is clearly positive. So I have the absolute value of x minus 2. And now I want to start to simplify. So in particular, I'm observing that this ratio leaves me with an extra factor of 2 in the top. So I have 2 times k plus 1 squared over k plus 2 squared. So here I have a polynomial on the top and the bottom. The degree is 2 in both. So what I'm really looking at is my ratio of leading coefficients in order to find the limit. So this limit will approach 2 over 1, or 2. So I am left with the absolute value of x minus 2 times the constant 2. And now, in approaching it this way, I want to find the radius of convergence. And in order to do so, we need to compare what we end up with to 1. When we can claim that what we have is strictly less than 1, the ratio test guarantees convergence. Now, setting this up, I want to keep going until I can make a claim about x minus a. So remember, the idea of the radius is it's the number r, so that we're setting up this kind of approach. So in this case, right now, we have this extra 2, but I can divide both sides by 2 and get to this point here. So once I've isolated x minus a, an absolute value, on one side, what is on the other side of the inequality is my radius. Now, what I want to point out is that you could have tackled this without rewriting the original series, and I'd like to just make that clear. So we're not done, because I need to go back and consider the interval. So I'll point out, what is the interval? So while I can certainly construct an open interval right now, I need to decide if the endpoints are included or not. Now, this is just an aside. So what I wanted to point out is, suppose you didn't rewrite the series in this way that we have in red. So coming back to this, you could still jump right into the ratio test, but I want to point out, so that we can avoid some confusion, what you would just have to be a little careful with in doing it that way. So if I were to use the ratio test on the representation of the series in its original form, I could do so. I would have absolute value of 2x minus 4 to the k plus 1 over k plus 2 squared times k plus 1 squared over 2x minus 4 to the k. So this would give me an extra factor of 2x minus 4 times the limit of just k plus 1 squared over k plus 2 squared. And notice that this limit now is 1. So the ratio of leading coefficients for this is just 1 over 1. So in approaching it this way, using the ratio test, we would be left with 2x minus 4 in absolute value. And we want to consider when that's less than 1. So a common mistake here is to assume, okay, I have this inequality. It must mean that what's on the right side is the radius. But we're not done, because this here is not of the form x minus a in absolute value. So I'm referring again to the significance of the radius. The radius is what sits on the right-hand side when you've reduced the left-hand side to the absolute value of x minus a. We can still get there, so we just need to know that we're not done. So I'm recognizing that this is 2 times the x minus 4 in absolute value here. And in that case, what I'm thinking of is dealing with that 2. Oops, I'm sorry, this should be a 2 if I factor that 2 out. And again, ending up at the same conclusion. So if I don't simplify my series in the beginning, that's fine, but just be careful about what your end goal is going to be. Where do you want to end up? Now, in either way, we end up with the conclusion that r is 1/2. That's what we found before. So what I want to come back is, how do we fill in the interval here? So what we know at this point is thinking about the fact that the center is 2. I know that the radius is 1/2. So I can move out by 1/2 on either side. So come to 3/2 and 5/2. And recall that what we know for sure is that this series has to converge everywhere inside of this interval, and it has to diverge everywhere outside of this interval. But we have to be very careful about what happens at what we're calling the endpoints here. So I'm talking about these. Do we include those or not? And so we said before that there are really 4 possibilities, and we always handle these endpoints on a case-by-case basis. So part of the goal here is, once you find the radius, figure out the value of the endpoints. And remember, I got to those by starting at the center and subtracting and adding the radius. And so we have to check the endpoints. And I really want to emphasize this, because this is commonly overlooked in these problems. So I cannot make any assumptions about the convergence at those endpoints, because that is where the ratio test would yield the limit 1. So checking my endpoints, what does that mean? So one of the endpoints was x equals 3/2. What I want to do is go back to my original power series, and in fact you can look at it in either the original form or the simplified form. And what I want to do is plug in the value of x that the endpoint gives me. So if we do that, let me use the simplified version. I'm going to get here the sum from k equals 0 to infinity. I have 2 to the k and k plus 1 squared in the denominator here. And I'm plugging in, so recall we had x minus 2 to the k. Well, I'm plugging in x equals 3/2. Now, notice what we get. We get 2 to the k. This becomes minus 1/2 to the k. And so I can simplify this by recognizing that the top would become just minus 1 to the k over k plus 1 squared. Now, this is an alternating series. So if I need to decide if this series converges or diverges, I can simply check the conditions of the alternating series test. So one is that the terms and magnitude go to 0 as k goes to infinity. We can see that that's true. And the other is that they are decreasing in size. And so by recognizing that the denominator on the left is larger here, I can see that's true as well. So what I get from this is that this series converges by the alternating series test. Now, once I have that, that tells me that I'm going to include this point in my interval of convergence. Let's check the other endpoint, which was 5/2. And again, to do so, I go back to my original series and I plug in x equals 5/2 for x. In this instance, we get 2 to the k times positive 1/2 to the k in the numerator. That reduces to 1 to the k, but of course I can just write that as 1. So this is the sum from 0 to infinity of 1 over k plus 1 squared. So I want to point out here that in fact, if I were to write this starting at 1, this is the same thing as just 1 over k squared. This I know converges because it's a p series with the value of p being strictly greater than 1. So now I see that this series converges as well. So I would want to include x equals 5/2 in my interval of convergence. So with all of that, in writing my interval, like I said, what I want to do is include both endpoints. So I put the square brackets here. Okay. So what I'd like to do is look at just 2 more examples that are related, or whoops. Actually, let me look at one more example that's a little bit related. So this notion of going through and finding the power series, radius, and interval of convergence. We have to be a little careful if it's presented in a slightly different way. So consider the power series now, which is the sum from k equals 0 to infinity of x to the 3k over minus 8 to the k. If I want to find the radius and interval of convergence, again, I would start by using the ratio test. And one thing that's significant here is the fact that we have this 3k in the exponent. Basically, what that's a reflection of is the fact that we'll have a constant term, an x cubed, an x to the 6, and so on. So we're getting several coefficients that are 0 along the way. In finding now my next term, again, I have to think of this as substituting in k plus 1 for k, making sure that I do, in fact, distribute that 3 through there. And I'm going to multiply by the reciprocal. So writing this, what I want to notice is I really have x to the 3k plus 3. And in thinking about how to simplify that here, we get something different than what we've seen in the previous examples. So it is true that I can bring out the absolute value of x in some way. But notice that what happens when I simplify this is I actually get an extra 3 of them. So thinking about the x cubed. So when I bring that outside of my limit in this instance, I'm really going to bring out the absolute value of x cubed because of that. What is left is we have this minus 8 to the k over minus 8 to the k plus 1. Here's where the absolute value is important here. I don't care about the negative. What I do care about is that there's an extra factor of 8 in the denominator. So because of the absolute value, again, I just put a positive 8 down there. And we want to know now when this is strictly less than 1 in order to guarantee convergence by the ratio test. This is the same thing as asking when is the absolute value of x cubed strictly less than 8. And that's going to happen when, so maybe let me pause here. Again, kind of like we talked about before, knowing that we're not done yet because my goal is to end up with, so the center here is 0. We need to end up with an inequality that looks like this. So that's going to require a cube root so that I have the x value being strictly less than the cube root of 8, which is now 2. So what we find here is that the radius is 2. So what I wanted to demonstrate with this example is that sometimes it's not a simple just k that we have in the x to the k as the part that deals with x. So we have here a 3k, and that involved us having to take a cube root. But now I'm at the point where I have my radius. I would want to, again, think about endpoints. In this example, the center is 0. Our radius is 2. So when I think about what the endpoints would be, I can see that they're going to be plus or minus 2. So in order to get the interval, I would have to, again, check my endpoints. And that requires me to plug them in one at a time. So if I look at -2 and plug that into my original power series, that's going to give me -2 to the 3k over -8 to the k. Notice that -2 to the 3k is -2 cubed to the k. That's just -8 to the k. So what happens here is this simplifies to just the sum of a series whose terms is 1. You could think of this lots of different ways. You could think of this as 1 to the k and say that it diverges because it's geometric with r an absolute value equal to 1. And of course, we need strictly less than 1 to converge. You could also use the test for divergence to say that the terms don't go to 0. But one way or another, we're going to see that we get divergence on that. If I look at the other endpoint, plugging in +2, that will become 8 to the k in the numerator. So when I simplify, that leaves me with -1 to the k. And again, one way to justify this is that we have a geometric series with the absolute value of r is equal to 1, or again, using the test for divergence. But in either instance, what we're seeing is that the interval for this example does not include the endpoints. So I want to leave those as parentheses instead of the square brackets. So with these, I think practice is really, really important. So again, I really encourage you to do the textbook problems here so that you know how to deal with lots of different things you might encounter. And just getting that practice, and like I said, really making sure if the radius is not 0 and it's not infinity, then you will have endpoints, and always knowing that you have to really check those on a case-by-case basis.